Hello everybody and welcome to the 7th lecture of MHM 427 AVT as well as MUA 782. So we spoke about fundamental of thermal radiation and radiation heat transfer. So we finished team 1. We wrote test 1 and these two section or first study team. You also wrote 2 assignments. In this lecture we are going to start team 2 and we are going to talk about boiling and condensation. Basically, as you can see here, we are going to speak about boiling heat transfer, pool boiling, flow boiling, condensation heat transfer, film condensation inside horizontal tubes, and drop-wise condensation. We will focus on convection processes associated with change in fluid phase. In particular, we will speak about processes occurring at the solid liquid or solid vapor interface, namely, as I mentioned, boiling and condensation. For these two cases, boiling and condensation, both of them, latent heat effects associated with the phase change are significant. The phase change from the liquid to the vapor state due to boiling is sustained by heat transfer from the solid surface, and condensation of a vapor to the liquid form results in heat transfer to the solid surface. In addition to latent heat, or as you remember or recall from thermodynamic HFG, the HFG value of water varies temperature, as you can see, you can remember from thermodynamic, you can read it from the table. This heat, latent heat, and two other parameters are important. One is surface tension at the liquid vapor interface, and the other one is density difference between the two phases. So it's not just latent heat, so surface tension as well as density differences between the two phases are important for us as well. I'm sure you can remember that this density difference induced buoyancy force. If you remember, which the buoyancy is proportional to density difference. Let me just write it here. If you remember, it was like something like this: rho L minus rho V, liquid state and vapor state. So due to the combination of latent heat and buoyancy driven effects, boiling and condensation heat transfer coefficients are generally larger than convection heat transfer without phase change, which does make sense. Before going deep into this chapter, I would like to speak about evaporation and how it is different from boiling, to avoid any confusion. Because sometimes I see that the students, they are a little bit confused regarding the differences between evaporation and boiling. Boiling, if you recall, just I told you 1 minute ago, occurs at the solid liquid interface when a liquid is brought into contact with a surface maintained at a temperature greater than the saturation temperature of liquid. So let me write it down because it's much easier. Okay, So we want to talk about the difference between evaporation and boiling. So I said that the boiling occurs at a solid liquid interface. When it happens, this is where boiling happens at solid liquid interface. When it happens, liquid is brought into contact with the surface that is maintained at a temperature greater than saturation temperature of liquid. Okay, so basically boiling happens at solid liquid interface. When boiling happens when the liquid is brought into contact with a surface that is maintained at a temperature greater than saturation temperature of liquid. So T surface greater than T sat liquid. So now we define boiling. We said that evaporation is different from boiling. So how different? So different might be the place that happens or when it happens. Am I right? Because we define boiling based on those two concepts. So let's try to define evaporation based on the same concept as well. So first we want to know that where evaporation occurs. Where? At liquid vapor interface. When it happens? When the vapor pressure is less than that of the saturation pressure. Of the liquid at a given temperature. Why? Because we know that based on the table at the end of the textbook, we know that for different temperatures there are different saturation pressures. So basically when it happens, P vapor less than P saturation liquid. Okay, so now we understand the differences between boiling and evaporation. When evaporation occurs at the at the solid liquid interface, is called boiling. As I told you earlier, the process occurs when the temperature of the surface Ts, let me go back to the previous one, Ts surface, exceeds the saturation temperature T sat corresponding to the liquid pressure. So heat will be transferred from the solid surface to the liquid and will be expressed by Newton's law of cooling. So I think it's fair to say that, okay, Q dot of boiling is H Ts minus T sat then, which is equal to H delta T excess. We call it delta T excess. Watt unit has watt square meter. Okay, so basically that's it, very simple. But of course H here is not it's boiling heat transfer coefficient, so we show it the same, but of course it's different from H that we use for convection heat transfer. Vapor bubbles existence and growth depends on the excess temperature. The nature of the surface and thermophysical properties of fluid, like the surface tension. Okay, so let's write it down because it's very important to understand this concept. When we are speaking about boiling, you know, it's always there are different flow regimes. We are going to talk about it later, but why we are talking about bubble here? Because bubbles play major role in boiling and multi or two-phase flows, but the existence of bubbles and their growth depends on excess temperature. What is it? We just defined it here. Excess temperature, Ts, surface temperature minus T sat. So delta T excess is equal to T surface minus T sat. Depends to this one. What else? Nature of the surface. What does it mean, nature of the surface? Like material, the surface is from how the surface of how surface is smooth, for example, is not smooth. How does it work? It's like depends to the property of the surface, what material the surface is, the shape, if it's smooth, if it's not, and things like that. It also depends to thermophysical properties of liquid. Well, properties of liquid or fluid. We can write it down. Like what? Like surface tension, for example. But how surface tension can play a role? So the surface tension decreases when temperature increases. Does make sense? Yes. And it will become zero at the critical temperature. That is the reason why there is no bubbles during the boiling at supercritical pressure and temperature. Okay, you remember this one? Let me just show you. I think you can remember it from thermodynamic, but I'm going to show it again. So it's solid here, it's liquid here, vapor here, T critical and P critical. So critical temperature and critical pressure. We remember the definition of critical temperature. The critical temperature of substance, how we define it in thermodynamic. So to remind you, the critical temperature of a substance is the temperature that the vapor of a substance cannot be liquefied. no matter how much pressure is applied at that temperature or temperature above that. So after critical point, doesn't matter how much you increase the pressure, that vapor cannot be liquefied. As simple as that. So just keep in mind that the boiling process does not occur under the thermodynamical equilibrium condition, and that's the reason why temperature and pressure of the vapor in a bubble are usually different from the liquid ones. Okay, so what kind of information we can get from that is that the temperature of liquid and the bubble are not the same, the temperature difference. So it's the driving force of heat transfer between two phases. We know about it. Temperature difference is the driving force of heat transfer. If there is no temperature difference, there is no heat transfer. So when the liquid is at a lower temperature than the bubble, what will happen? So basically they are going to be two different conditions. The first one is temperature liquid, I just left liquid lower than temperature of bubble. Or T liquid is greater than. So in these two conditions, what will happen? So when the liquid is at the lower temperature than the bubble, so the first case scenario, what will happen? So in this case number 1, heat will be transformed from the bubble into the liquid. Does make sense? Yes. Heat goes from a phase or material a higher temperature to the lower one. So heat will be transformed from the bubble into the liquid, which will cause some of the vapor inside the bubble to condense and the bubble will collapse. But if the liquid, the temperature of the liquid is at a higher temperature than the bubble, or case number 2 here, what will happen is that heat will be transformed from liquid to the bubble. Then bubble will grow and rise to the top of the surface under influence of buoyancy. Let's talk a little bit about boiling classifications. Just keep in mind that those are like a very basic information that I'm giving to you. After that, we are going to go and talk about all different aspects of boiling and condensation. So boiling can be classified into pool boiling, so boiling, pool boiling, what else? Flow boiling, I mentioned it at the beginning, flow boiling. These two. But what are their difference between like pool boiling and flow boiling? Because when we categorize boiling into these two, most probably they should have some kind of differences. Am I right? So flow boiling is based on the presence of a bulk flow motion. So when we have a bulk fluid motion, that boiling is flow boiling. But when there is no bulk flow motion, It's called pool boiling. In pool boiling, fluid is stationary, and any motion of the fluid is due to the natural convection currents and the motion of the bubbles under the influence of buoyancy. So when we are speaking about pool boiling again, let me just start a new page to write it down again, maybe cleaner for better understanding. So I said that the pool boiling, when there is no bulk fluid motion, and flow boiling when there is presence of soft bulk fluid motion. Okay, we just said that pool boiling, when the fluid is stationary, and any motion of the fluid is due to natural convection, and motion of bubbles are due to buoyancy. Okay. Can you give me one example of pool boiling in a daily life? Let's say the fluid is stationary, there is no bulk fluid motion, any kind of movement inside the fluid is due to natural convection currents, and motion of bubbles is under influence of buoyancy. Yeah, boiling of water in a pan or on top of a stove. That's one of the best examples of pool boiling. Pool and flow boiling can also be classified as sub-cooled boiling or saturated boiling, for both of them, which depends on the bulk liquid temperature. When the temperature of liquid is below the saturation temperature, the boiling is called subcooled or local boiling, and when the temperature of liquid is equal to the saturation temperature is saturated one. Saturated temperature is the temperature which the vaporization occurs, okay? But let's focus on pool boiling. What we know so far about pool boiling. We know that first, pool boiling occurs when the fluid is stationary, so it means that the fluid is not forced to flow. 2. We also know that any motion of the fluid is due to natural convection current and the motion of the bubbles under the influence of buoyancy. So that's it about the pool boiling. Let's go back to the classic example of pool boiling. Tap water in a pan on top of a stove. Okay, let's see what will happen here. Okay, forget about those like natural convection boiling or nucleate or transition boiling or film boiling. Just focus on what am I saying. So you have a tap water in a pan on top of a stove. Let's assume that the initial temperature of water is around 15 degrees. 15 degrees is far below the saturation temperature of water in atmospheric, which is around 100 degrees, like the saturation temperature. So at the early stage of boiling, nothing significant is noticeable, just some bubbles that are sticking to the pan surface. Those bubbles are caused by the release of air molecules dissolved in water, and don't confuse it with vapor bubble. Okay? Don't think about that nuclear. As the water temperature increases, chunks of liquid water rolling up and down due to the natural convection current. Soon after that, the first vapor bubble will form at the bottom surface of the pan. Those bubbles get smaller as they detach from the surface and start rising and eventually collapse in the cooler water layers on top. This is subcooled boiling, since the bulk temperature of water has not reached to the saturation temperature yet. The intensity of bubble formation increases as the water temperature rises further. Okay? And you will notice waves of vapor bubbles coming from the bottom and rising to the top when the water temperature reaches the saturation temperature. This full scale of boiling is saturated boiling. But if we want to, like, different stage of the process that I told you has different names. So we are going to talk about it, and the majority of them, they are related to the temperature difference between T surface minus T sat, or delta T excess that we talked about. So we will have natural convection boiling, nucleate boiling, transition, and film boiling. We are going to talk about them, don't worry. Let's go to this figure. This figure shows the boiling curve of water at 1 atmosphere. So basically what we have is we have natural convection boiling, nucleate boiling, transition boiling, film boiling. Different parts we are going to talk about. We need to keep in mind that boiling is one of the most unknown forms of heat transfer, or very complicated one. Although many researchers are working on this topic and many papers has been published on boiling, but we still do not fully understand the process of bubble formation, and we still rely on empirical or semi-empirical correlations a lot to predict the rate of boiling heat transfer. Nukiyama in 1934 suggested this boiling curve and categorized the boiling process into 4 different regimes based on the excess temperature. This curve is for he worked on water at 1 atmosphere, but the shape will remain more or less the same for different fluids, but of course there are some differences, but the shape and trend is more or less the same. As you can see, the 4 regimes or regions of boiling are natural convection boiling, nucleate boiling, transition boiling, and film boiling. Now we are going to discuss each of these regimes in detail. Let's start with natural convection boiling. From thermodynamics, we know that a liquid starts boiling when it reaches the saturation temperature at a given pressure. Do you agree with me? It's from thermodynamics, you passed the course, so it's not a very complicated one. So liquid starts to boil when it reaches the saturation temperature at a given pressure. But in practice, the bubble formation on the heating surface starts when the liquid is heated a few degrees above the saturation temperature. For example, here you see that for delta T excess, like let's say 0 or 1, when the surface temperature is equal to T sat, nothing is going to happen. But when we are increasing the temperature from 1 to 5, like the surface temperature is 1, 2, 3 to 5 degrees higher than saturation temperature of the liquid. When that happens, the fluid motion in this condition will be due to natural convection currents, and heat transfer from the heating surface to the fluid is by natural convection. As you can see in the picture, natural convection boiling ends at point A, which has the excess temperature of 5 Celsius. Between point A and point C, which is nucleate boiling, between these two we see another point B, that there is like a kind of distinction between point A, point B, and between point B and point C. There is like a little bit of information here that it says between point A and B bubbles collapse in liquid, but between B and C bubbles rise to the surface. Okay, we are going to talk about it. As we move along the boiling curve toward point C by increasing the excess temperature, the bubble formation as well as the nucleation sites will increase. From the picture, we see that nucleate boiling has been divided into two subsections, as I mentioned, A to B, 5 delta T excess 10, and B to C, 10 delta T excess 30. Now let's speak about why we have these two subsections here. In the first region, between A to B, isolated bubbles form at nucleation site on the heated surface and separate from the surface. This separation induces fluid mixing near the surface, which will result in higher H or heat transfer coefficient and consequently higher Q dot boiling. In that region, I mean A to B, most of the heat exchange is through direct transfer from the surface to liquid, not through the vapor bubbles rising from the surface. But when the delta T excess is increased beyond point B, more nucleation sites become active, and increased bubble formation will result in bubble interference. In the second region, from B to C, the heater temperature is further increased, like the surface temperature, and bubble formation rate will increase as well. Higher bubble formation rates result in larger number of nucleation sites that form continuous columns of vapor, as this condition showed here. These bubbles move all the way up to the surface, where they break up and release the vapor content. The large heat fluxes in this region is due to the combination of liquid entrancement and evaporation. So we talked about this section, A to B and B to C. At larger values of delta T excess, the rate of evaporation at the surface reaches to a value that a larger fraction of the heater surface is covered by bubbles. Okay. So what will happen is that you see here there is like a layer is covered like a, this is making it difficult for liquid to reach to the heater surface and wet it. Consequently, the heat flux increases at a lower rate with increasing delta T excess and reaches a maximum point of C. The heat flux at this point is called the critical or maximum heat flux, or CHF. Due to having the highest heat transfer rates with delta T excess, values lower than 30, nucleate boiling is the most desirable boiling regime in practical application. So what does it mean? It means that, okay, I want to design something by using the concept of boiling. What I want to have the highest Q dot boiling. Am I right? So I'm going to design it for this part between B and C, and I would like to design it as close as possible to C. This area is the best, but when we go closer to the C, it's better. So the C, it's the maximum or critical heat flux. But after point C, as you can see, we call it transition boiling. Q dot boiling drops. But why that happens? As the excess temperature goes beyond point C, the heat flux decreases. Why? Actually, I mentioned the reason when I was speaking about the nucleate boiling. As I told you, when the heater temperature, or like the temperature of the surface, increases, a large fraction of heater surface will be covered by a vapor film, which work like a layer of insulation. Why? Because vapor has lower thermal conductivity compared to its liquid form. Look at here, the layer. So because this layer works like as a kind of like insulation layer, so Q dot will drop. In the transition boiling regime, nucleate boiling and film boiling are happening simultaneously. So in this transition boiling, that's the reason we call it transition. So film boiling and nucleate boiling, they are happening simultaneously. Going from point C to D will increase the percentage of film boiling from 0 to 100. So here, so we have nucleate boiling, so let's say 100% to 0 film boiling. But when we are going to walk through point D, when the temperature increases, so the percentage of film boiling is increasing from 0 to 100 up to this point that we call it Lorenfrost point. It's Q dot minimum, and after that any increase in surface temperature or increase in delta T excess will result in higher Q dot boiling. And of course it's a film boiling after point D. In this region, I mean after D or the film boiling, this region, the heater surface is completely covered by a stable vapor film, and that's why the heat flux reaches a minimum point at D, because at point D that layer, insulated layer, is completed. The point Lorenfrost, we call that point, and it's in honor of the first person observed it. The vapor film between the heater surface and the liquid is responsible for this very low heat transfer at the beginning of the film boiling regime. But how the picture is showing an increase in heat flux beyond the point D? To answer that, we can say that when the excess temperature increases beyond point D, which is around 120 degrees, it means that 120 degrees, the surface temperature is higher than the saturation temperature of the liquid. So it's not just 120, it's 120 higher than that of the saturation temperature of the liquid. Heat transfer from point D like from surface to the liquid occurs by conduction and radiation through the vapor. Like how it's possible, conduction and radiation? Why radiation? Because of the high temperature. But how about conduction? Do you have any idea why conduction will happen there? It was Lorenfrost that observed it in 1756. Just think about that. 1756 is almost 250 years ago. That water droplets supported by vapor film slowly boil as they move from the hot surface. He observed it. As the surface temperature is increased, radiation through the vapor film become more significant, and the heat flux increases with increase in excess temperature. But when this will stop, this process, because it continues up to the end? No, it can't stay forever. This can be explained by burnout phenomenon. To move beyond point C, which has the maximum heat flux, we must increase the heater surface temperature Ts, which will increase delta T excess. To increase Ts, we must increase the heat flux. But the fluid cannot receive this increased energy at an excess temperature just beyond point C. Therefore, the heater surface ends up absorbing the increased energy, causing the heater surface temperature to rise. Since the fluid can receive even less energy at this increased excess temperature, the heater surface temperature has to rise even further. This continues until the surface temperature reaches a point at which it no longer rises and the heat supplied can be transferred to the liquid steadily. This is point E on the boiling curve. It's like you can see it here, which occurs, as I mentioned, the process. If we want to get another maximum in heat flux, we need to reach to point E, which is beyond the melting point of most materials. So you see that why we first said that the best designing point or section for us is between B and C. Why? Because yes, that's true that at point C or points closer to C, we can get the same Q dot, but with what price? Let's say 1200 or 1300 degrees higher than the saturation temperature of liquid, while we could get the same Q dot by around 25 or 26 temperature higher than the saturation temperature of the liquid. So we study about it because we want to avoid it, not because it's desirable for us. Okay, just keep it in mind, because that can help you how to understand it in a like engineering way, that why we are learning this boiling heat transfer, and we are talking about the curve, because now you understand when you want to design what area you need to focus. So as you can see here, we discussed these 4 different boiling regimes. We talked about natural convection boiling, nucleate boiling, transition boiling, and film boiling. But it was just like talking. At the end of the day, what we want to find out or calculate is Q dot boiling. We want to find Q dot boiling. We want to find H or calculate H, which is boiling heat transfer coefficient. So we want to find numbers. We want to find out what's the Q dot max in terms of like a number to find the maximum heat flux. We want to find the minimum heat flux. We want to calculate the Q dot mean, which happens at the Lorenfrost. So I think that's enough for this lecture. In the next lecture, we are going to talk about correlations that we can use to find Q dot boiling for different flow regimes, like natural convection boiling, nucleate boiling, transition boiling, film boiling. We are going to talk about those correlations and how we can calculate.